Hello everyone, this is video cam 001. My name is George Okolo. I'm a PG student in Engr State University of Science and Technology. I'm here to do one of my practicals, which is on the EEE 624, Electronic Devices and Systems. The title of the experiment is the design, simulation, and construction of a 9-volt DC zener regulated power supply. And I have my components as you can see them here. I have my transformer, my capacitors, zener diode, 9-volt zener, and some regulators, some rectifiers, diodes, and other capacitors here. I have some resistors as well. The aim of the experiment is to design and simulate and eventually construct a 9-volt zener regulated power supply that will power a 2-stage transistor small signal amplifier. Okay, here, as you can see from the simulator, the Proteus simulator here, I have done this, but the initial circuit diagram that was given to us is this. You can see in the circuit diagram, it has a supply voltage, that is incoming voltage, which is AC at the level of 220. And the circuit diagram has a fuse, but it doesn't have a switch, which is very essential. Okay. So it has a transformer. This is a 12 volts transformer, and it have a bridge type of rectifiers comprising D1, D2, D3, D4. And the value for this is IN4001 that was given. Okay. And it has a 1000 UF capacitor. And you can see the value of the diode, D1 to D4, IN401. You can see the value of the zener diode, which is the regulator. Zener diode, which is the regulator, 9 volts. And you can see another smoothing capacitor, 0.1 microfarad, and this is the V out. Unfortunately, going to the market to search for the components, we didn't get all the components as specified, but we made use of equivalent. In doing this, you have to check that the parameters match. For instance, I didn't see a diode IN4001, but I had 4007, IN4007, which has a reverse breakdown voltage of 1000 volts, which is also good, which has a because the germanium PN junction voltage of 0.7, which is equivalent to this. And in fact, IN4007 is a higher capacity diode than this, which made it very good for me to use. I got a transformer, which is this is a 0.5 amp, which is 500 milliamps. So I got a transformer 12 volt by 220, which is 500 milliamps. That was okay. I had a fuse, 500 milliamp fuse, and because this is 12 volts and I need a 9 volts here, okay, I chose my capacitors to be above 12 volts. So I chose 1000 UF by 16 volts. And another one, I chose this 1000 UF is equivalent to 100 nanofarad. That's exactly what I use in my simulation, as you can see from my Proteus. So here, in my Proteus, I have my transformer, which is the AC source, which is 220 AC. I have my switch and my fuse. Okay, here, this is my transformer. It is a 12 volt transformer. That is 12 volt step down transformer. And in my rectifier, bridge rectifier, I have IN4007. The characteristic is such that it has a reverse breakdown voltage of 1000 volts DC, which is normal. And you can see new introductions in the circuit diagram. I introduced R1 is a series or limiting resistor. This functions to minimize the current to fall within IZ min and IZ max, which is suitable for zener to function properly. When I omitted it, what I got in my output is not up to 9 volts. It was plus 5, but I had to introduce this limiting resistor that will give me that. Now, my C1 is 1000 UF by 16 volts. My C3 is a ceramic capacitor, which is a high pass capacitor, which is meant to filter off more of the ACs to allow for a steady and smooth straight DC. Beside it is my zener 9 volts diode. That my zener diode is a high capacity zener diode. It has a wattage of it can handle 600 watts diode, because this is a zener regulated, very, very, very low power stuff, although we have high power zeners. Okay. And after the zener is another smoothing capacitor in case there are some ACs remaining. That is the 0.1 UF or the 100 nanofarad capacitor. Okay. So this is my experimental or simulated power supply, the one designed by me. And you have my DC voltmeter here. You have my oscilloscope here. And I can also connect my AC voltmeter here. So I am going to turn on this stuff so that we can measure. So turn it on. My oscilloscope comes up. Okay. My oscilloscope comes up here. Then I will have to switch on my circuit. So you can see. This is what you have in my oscilloscope. This is the main AC as specified by the connection here. Yellow is my AC, and that's my DC, and that's my DC, and that's my DC. Okay. So I had to adjust my oscilloscope to give me, I'm adjusting the horizontal. Put it at 10, no, too much, at 5. So you can see the waveforms clearly. Okay. So it's a bit it's a bit straight, but not that straight, which tells you that you still have some small AC in there. Okay. I'm adjusting level to see. Okay, you can see it's a pretty much distributed AC. And what is the output of my power supply? It is a 9.03 volts AC, which is perfect. 9.03 volts, perfect. Sorry. Okay. If I connect my AC meter, first switch off, then turn off the switch. There's safety precautions. One of the safety precautions, you must always turn off the switch and switch off from the AC mains before you do any connection. So I connect my AC meter. Remember, this is AC meter to AC. I want to, okay, it's the same potential here and the same potential here. I want to check the AC level output. Okay. Having done that, I'll have to turn on my scope again, or simulate. My scope comes on. You can see the switch is off. The switch is off. Nothing happens. Immediately I turn the switch on. You can see that. Okay. You can see that. So This is it. From my AC meter, I am getting an 8.5 plus 8.5. 8.51. Yes, it's supposed to be, which is 8.5 plus 9.5, because it's like a voltage divider stuff, which gives me about 15. And you know, 12 volts is just the peak, the RMS value of 12 times by root 2, 12 times by root 2, 12 times by 1.414 equals almost 16 volts, which is, yeah, 16.9999, which is exactly what you get, what you add 9 plus 8 here. Okay, so 9.03 plus 8.51 is almost 17 volts, you know, give or take, or small resistances here. So this is what I've been able to achieve. Now, next up is the calculations. I'm going to do the reporting, my part listing, and considerations for the choice of equipment, after which I'll now do the, oh, sorry. This is funny sometimes. After which I will do the main, turn it off button. Right, I switched off and there it goes. So thank you. As I said, thank you very much, sir, for your time, and thank you for this opportunity. Yes, next up, I am writing my report and, building the stuff. This is part 1 of this video. Part 2 will is basically the small signal amplifier stage, after which I will build everything on the same breadboard and connect everything together and test. Meanwhile, I hope to build everything on this page, the power supply and small signal amplifications, and I'll connect everything and test. Thank you very much. Thank you. My name remains George Okulu, 2017, 2018 PG student. Thank you very much. Thank you.